Hey friends, today let us start with a new topic, that is action potential in a muscle. Before I start with the action potential in a muscle, let me give you an idea of resting membrane potential but in brief manner. So resting membrane potential is basically the polarized state of a muscle in which there is more negativity inside and the more positivity outside the muscle cell. Let me show you in this diagram that, let's suppose this is a muscle fiber and in which there is more negativity inside the muscle fiber and more positivity outside the muscle fiber. So the more negativity inside, more positivity outside, this is known as the polarized state of the muscle, and the action potential, which is a potential difference across this particular cell membrane, that is the resting membrane potential, and this remains constant until a stimulus is applied to it. Now let us understand the action potential. So let me give you some information which is very basic before we start the actual topic, that is action potential. So action potential, first of all, it is an electrochemical changes occurring in the cell membrane. Second thing is, action potential is generated when a stimulus is applied to the muscle fiber, or I can say over the muscle membrane. Next thing is action potential which is self-propagated. Okay, so it travels in the cell membrane. Okay, so this is the basic information regarding the cell membrane. Now let us understand what are the ionic bases and how do we actually analyze the action potential as a topic. So suppose this is the next muscle fiber we have, and I am going to apply a stimulus to this. So suppose this is a stimulus which I have applied to the muscle membrane. Now what happens is, at the point of stimulus, the sodium ion channels which are there in the cell membrane, so they open up. More and more sodium ions, they are going inside of the cell membrane, and another thing, that is the potassium ions, they are going back through the potassium ion channels. Right, so these are the channels which are already present in the cell membrane. When we apply a stimulus, there is opening of the sodium gated channels and as well as opening of the potassium gated channels. So there is influx of sodium ions and efflux of potassium ions. So let me write it over here, that there is sodium ion influx and potassium ion efflux. So sodium ions are coming in and the inside of the cell is becoming more and more positive. So let me write it over here, that inside of the cell it is now positive and outside becomes negative. Right, so now you can see that from the resting condition, by applying just a stimulus, the inside of the cell becomes more positive and outside of the cell becomes more negative, which is exactly opposite to the resting membrane potential, or I can say the polarized state of the muscle. Now let us understand the graphical representation of the action potential, that actually what is happening when we apply a stimulus. So let me draw a graph over here in which over the y-axis we will take amplitude. Let me write it over here, that is amplitude in millivolts, and over the x-axis we have time in millisecond. Now what happens is, before I start explaining you this graph, I will explain the graph according to the ionic changes which are occurring in this particular cell membrane. So do focus on the graph as well as the cell membrane changes, as it is electrochemical changes, so we must focus on the ionic exchange continuously. Now in the resting condition, if we measure the polarized state by a cathode ray oscilloscope, which is a device, so for the muscle, particularly the skeletal muscle, the resting membrane potential is about minus 90 millivolts. For the resting condition, for the skeletal muscle, resting membrane potential is minus 90 millivolts. Now, in this minus 90 millivolts, if I apply a stimulus, what is going to happen? Let's see that. Suppose here I have a marking that is minus 90 millivolts over the y-axis and at the 0 millisecond time. Now I have applied this particular stimulus. What is going to happen? Initially the no changes will be there, right? And this is the phase which is known as an latent period, right? So let me write it over here, that this typical phase is known as an latent period, right? So in the latent period, the no changes occur in the cell membrane. Now comes the a small sub point in this, that is stimulus artifact. What is the stimulus artifact? Let me write it over here. This is a stimulus artifact. Stimulus artifact, it is nothing but it is a slight irregular deflection in the baseline of the graph of the action potential, right? So this may show in some of the graph and it may not present in some of the graphs, but for this we need to understand that stimulus artifact, it is a slight irregular deflection in the baseline of the graphical representation of action potential. Now what happens is depolarization starts. Depolarization means what? Opening of the sodium gated channels, opening of the potassium gated channels, there is more positivity inside. So from minus 90 millivolts, if I need to show a positivity inside the cell membrane, how do I draw my graph? That initially it will rise up, right? So suppose it reaches to the some extent minus 60 millivolts. So there is slight increase in the positivity inside the cell membrane, and whenever positivity increases inside the cell membrane, we call it as a depolarization. But in this depolarization, there is a point which we call it as a firing level. Firing level. So what is the importance of this firing level? That firing level shows that from this point your graph is going to rise up to its maximum. That what happens is, if I start counting from here, minus 90, minus 60, then comes minus 40, and up to this some extent, here comes a 0 millivolt. At the level of 0 millivolt, I draw this line which is known as an isoelectric base. Isoelectric baseline. Now what is this isoelectric baseline? Isoelectric baseline suggests that there is a 0 millivolt potential, means 0 amplitude is there, 0 millivolt potential is there. Now when your graph, after crossing the firing level, it is going upwards, so more and more sodium ions are opening up and there is more positivity inside, so more entry, or I can say the concentration of the sodium ions is present inside the cell membrane. So the maximum point which is over here, which is achieved by this graph, that is plus 55 millivolt. That is the highest point achieved by our cell membrane. Now this particular level is known as an overshoot. Let me write it over here, that this is overshoot. And this process, it is occurring very rapidly. So this particular line, starting from the stimulus artifact up to the overshoot, this is showing the rapid depolarization. Rapid depolarization. Now once the stimulus is applied, all the sodium ions are opened up, there is more concentration of the sodium ions inside. Now there is reverse of this is going to occur. That is, this particular cell will now try to achieve its position, that is the pre-stimulus position, that is again the resting membrane potential. We call it as a repolarization. So in the repolarization, what is going to happen, that inside of the muscle becomes more and more negative and outside of the becomes more and more positive. So exactly opposite to the action potential is going to happen in the repolarization. Now how does this occur? So initially all the sodium ions channels, sodium ion voltage gated channels were opened up because of the stimulus applied. Now what is going to happen, that more and more potassium ions, they are going outside. The sodium ion channels which are present in the cell membrane, they open up for a very short period of time. But for the potassium ion channels, these are also known as a leaky channels. Leaky channel means they will remain open for prolonged period of time. Now what is going to happen, initially when positivity was inside and the sodium ion channels, they were open and rapidly closed because depolarization is now over. But potassium ion channels, or I can say the leaky channels, they will remain open for further duration of time. So more and more potassium ions, they will start going outside of the cell membrane. So the positivity is going to decrease slowly and gradually. So after watching over the rapid depolarization, which is followed by a very slow repolarization, let me draw it over here, that a very slow repolarization is going to happen, and a graph from the plus 55 millivolts, it is going downward because there is more negativity inside. If negativity is increasing, then the downward slope which is seen, it is because of the repolarization. So let me write it over here, that this is a very slow repolarization. And in this very slow repolarization, after achieving the minus 90 millivolt, you can see that the graph is also going further downwards. So this is known as a hyperpolarization. Let me write it over here. This is known as an hyperpolarization. Right? So hyperpolarization, so which is actually suggesting that now this typical cell is now again ready. If a stimulus is applied to it, it will again start from minus 90 millivolt, reaching up to the plus 55 millivolts, then again going further after hyperpolarization. Right? So rapid depolarization, which is followed by a rapid repolarization, so we combine these two, is known as an spike potential. So if I draw a box like this, then the combination of these two is known as an spike potential. Right. I hope you are clear with the ionic changes as well as the graphical representation. So we must revise this concept, that when a stimulus is applied, the sodium ion channels, they are opened up, and already in the cell there are sodium ion channels as well as the potassium ion channels, they both are already present. But for a very short duration of time, sodium ion channels are opened up. Maximum number of sodium ion channels, they are coming in, decreasing the negativity inside the muscle membrane. So there will be more positivity and the graph is steeply rising up to the plus 55 millivolt, and we see a rapid depolarization. Now followed by this rapid depolarization, we saw a very slow repolarization. What is the reason behind it? Reason is very simple, that in the cell membrane we have some leaky channels which remain open for prolonged period of time. So once the depolarization is accomplished, a slow repolarization starts, and this very slow repolarization, which is suggesting of the positivity, is slowly gradually going out of the cell through the leaky channels. So that was the reason behind the repolarization as well as the depolarization. Now you must be thinking that I have explained for a single cell only. Now how does the action potential propagates into the next cell? Right? It is a very natural question that should occur in our mind, that if I'm explaining for a single muscle fiber and I explain that this action potential, it is self-propagated. So there must be connection between the two cells, right? Remember, if you watch this video again, you will notice that I have not mentioned that sodium ions are going outside in the extracellular fluid. Right, so the sodium ions, a small amount of sodium ions which are inside the cell. So in our body there is a gap junction in between the cells. So those sodium ions, they will travel through the gap junction and take an entry into the next cell, and again they depolarize the next cell membrane, and again the action potential starts. So this is how from cell number 1 to the cell number 2 the action potential is propagated, or I can say that transmitted, and this is how our muscle, they are stimulated. Now another thing is that if you have watched my previous videos, I have explained about the sarcotubular system. Right, there are many T tubules and the L tubules. Now what if I combine the concept of sarcotubular system with the action potential? So let's see that thing. Let me rub all these things. In the sarcotubular system, I have explained that T tubules and L tubules, the both tubules, they are present, right? So if I draw a muscle cell, right, so for example this is a muscle cell which is cylindrical in shape, obviously, and for example I am drawing it over here, that this sarcotubular system is exactly overlapped over the muscle fiber. But for explaining you the combined concept of the sarcotubular system and the action potential, I am drawing it like this. So here we have, first thing is a bulge portion, that is L tubule, we have T tubules, then again a L tubule, then again a T tubule, then again a L tubule, and this is the T triad, which is the cisternae, then the T tubule, then again the cisternae, right? So when an action potential comes, now comes the most important thing, that when an action potential comes, it strikes over the sarcolemma. Sarcolemma has multiple opening of the T tubules. So actually what is going to happen, that I am going to explain in my next video, that is the neuromuscular junction, that when an action potential comes, there is a neurotransmitter named acetylcholine. So that acetylcholine, when it strikes over that sarcolemma, right, so it is going to stimulate the sodium ion channels which are there in the presynaptic membrane, or I can say over the sarcolemma, right, and they spread, action potential is spread over whole of the sarcolemma, and sarcolemma has pores, right, it is a membrane shows as the pores, and these pores are what? They are opening of the T tubules. Now this T tubules, when the action potential is completely spreaded over that sarcolemma, the pores are also get filled by this action potential, or I can say the what is that, is the acetylcholine, or I can say the sodium gated channels. So when the action potential reaches up to the end portion through this T tubules, first of all it passes through this T triad. So L tubule, from the L tubules calcium ion are going to release, and when the action potential is reaching up to this level, that it crosses the sarcolemma, many sodium channels, they are going to open up. Potassium channels, leaky channels, they remain open for prolonged period of time. That is not the point of discussion. But the calcium ions, they are going to trigger the excitation, contraction coupling theory, and the sodium ions which are going inside the cell, right, they are increasing more and more positivity inside the cell membrane. So I have already explained the actin filaments, the myosin filaments. Okay, the excitation contraction theory, or I can say the sliding filament theory, is going to happen because this thing, it was triggered by the calcium ions released from the cisternae, and they are reaching up to the level of contractile elements of the muscle, that is the tropomyosin, troponin, actin filament and the myosin filament. Four things are there in this muscle fiber. So that was the whole thing, that if we combine the sarcotubular system, contractile elements of the muscle and the action potential, this is how the whole concept gets cleared. If you are having any doubts, do let me know in the comment section. I am ready to give you the answers of this question. Spread these videos maximum so that one can understand and one can make link. Like today I have explained how do you make a link between the sarcotubular system, contractile elements of the muscle and the action potential. If you share these videos, some of your friends or your colleagues may start learning about this linking the concept technique. Right? I hope you like my content and the way of presentation. Thanks for watching the video till the end. Thank you so much.